Hi everyone. Today we'll be talking about where NoSQL databases can be used and why they're so popular. Yes, we will be talking about NoSQL databases and why they're the best in the world. And we're really excited about actually talking about this topic. Yes, there are a lot of scenarios where NoSQL databases are used. There are an equally high number of scenarios where NoSQL databases are not used. So it's important to know when to use them and when not to use them. Well, yes, whenever you're building toy apps, that time you need your RDBMS, but whenever you need scale, it's NoSQL databases. All right. That's not entirely true, actually. It's not that scalability demands a NoSQL database. There are certain scenarios when these databases tend to do well, and we'll be getting to them in this video. Could you give us an example? Well, YouTube doesn't use NoSQL databases. Stack Overflow doesn't use NoSQL databases. Instagram doesn't use NoSQL databases. WhatsApp doesn't use NoSQL databases. WhatsApp doesn't have a database. Let's start with the video. So what is the difference between SQL and NoSQL? Well, if you have a look at the database schema that we have for an example of a person, in which case they have an ID, that's the user ID. We have the name, address, age, and role. Now the address is a complicated object. So what I'm going to be storing, the way I'm going to be storing it is in a separate table. The address ID 23 corresponds to this row, which means that the address is Munich and in Germany, and the district is blank. So you're seeing that there is some sort of foreign key mapping here. And that's how we store data in SQL. This is how you store it in NoSQL. You have the ID 123, and you just have this big fat blob of data, right? This is JSON, and the way it stores it is the column name maps to a value, which is name John Doe, the same thing over here. The address is no longer a foreign key. The address is another object within this object. So that is just JSON, nesting. We have address, ID, city, and country. And because there's a null value of district, we actually don't even store that. We have the age and the role also defined, and you're seeing that there's this big blob of data over here. So what makes NoSQL so efficient? The key is to think about how we are storing and retrieving data. When we are storing data, usually it's never like a user registers and they send their age later on, or they send the role later on, or they send the address later on. It's all together. So when there is an insertion, there's usually all the fields inserted together, which means that this entire fat blob could have been written on the API. I mean, when the request was coming in, all this information was there, and you could have done this in a single insert. And whenever you're pulling out information about any user, usually you'll need all the information about that user, right? Select star is something so common that people don't even think about adding the column names these days, unless it's, of course, a very big table, or if you have some column which is pretty big and you want to avoid that, that's a separate scenario. But usually select star is very, very common. So because select star is so common, and because you need all the data relevant to a user all the time, this means that this entire blob will also be pulled out all the time. So that means insertions and retrievals require the whole blob. So why not keep it together? You see, when you're running a query on the SQL database, usually the pointer comes to, let's say, this ID, this row, and then it has to sequentially read all these columns. Not just that, you also don't have a clean way to denormalize things. Like this address could store the string, but this database is not inbuilt for denormalizing things. So you might need a join, which is pretty expensive, considering that most of the times you'll need both data. It's cheap over here, and that's the first benefit of using NoSQL, right? All your data, relevant data, is contained together in one block, and so it's a little easier to insert and retrieve. The second thing is that this schema is flexible. We saw that the district was null, and for this SQL approach, what we had to do is we have to add a new column. Although we don't need it, we still do it. Over here, what could happen is that if the address is null, if the address is entirely blank, that's fine, because this blob doesn't care about schema. All it cares about is a JSON document. So there'll be name, John Doe, comma, straight away age, 30, and the role is ST. So what you're seeing is that the schema is very flexible in this case, and not so much over here. In fact, whenever you're doing a new attribute addition, let us say that we have some new attribute added over here, which is salary. So whenever salary is added, we have to actually add a new column to this SQL database, which is a very expensive operation because you need some sort of locks on the table. And it's also risky to maintain consistency at this time. So, I mean, if you want to maintain consistency, then you need the locks. And that's the reason why it is expensive. While over here, if there is something that you're adding, which you don't need for all the older users, what you can do is just start adding them straight away. Because like I said, the schema doesn't care. The older schema doesn't know that there's anything called salary. Okay, so the second advantage is that schema is easily changeable. The third advantage of NoSQL databases is that they have horizontal partitioning inbuilt. Most of the times they expect a lot of scale to come in. I mean, the users for these NoSQL databases expect a lot of scale. So what they tend to do is they horizontally partition this data. Now you can have a look at the sharding video to get a better understanding of horizontal partitioning. And of course, when it is allowing this kind of partitioning, it's more focused on availability, which is a good thing. A lot of systems actually require availability over consistency. Yeah, so that's the good thing, built for scale. The fourth and final major advantage of NoSQL databases is that they're built for aggregations also. When a person is storing data in the NoSQL database, they're usually expecting to be getting some important information out of that data. For example, what is the average age? What is the total salary? These kind of databases are built for finding metrics and getting intelligent data. So that's what they're built for, aggregations. Okay, so these are the advantages that we have of NoSQL databases. What are the disadvantages? Not too many updates are inherently supported in this. So if you have lots of updates, this is not really nice. What are the possible problems here? Well, the data may not be consistent, meaning that the two nodes may have different data for the same ID. Yeah, while this SQL databases usually give you something called ACID properties, by which you can contain this issue. So that is a problem. So I'll just write it down. Consistency is a problem, which basically means ACID is not guaranteed. If ACID is not guaranteed, you can't have transactions using NoSQL databases. At least you can't have the same transaction properties of ACID. Okay, so that's a big reason why financial systems don't use NoSQL databases for their transactions, because it doesn't make much sense. The second problem is that these databases are not read optimized. If I ask you to find me all the ages of all the employees that we have in the company, what's going to happen is it's going to go to these blocks, and each time it's going to read the entire block, then filter out the age and do that for every row, then return you the result. While in a SQL database, all you need to do is just come to this column. I mean, it won't be that easy. The reader has to actually go to that column and then read that column. But this is more efficient than this. So these are not read optimized. Read times are comparatively slower. The last two problems I can see here is that this does not have implicit information about relations. So in an RDBMS, the R stands for relation. Now, 23, the address ID, maps to this point. And what that tells you is that this row is somehow related to this row across the two tables, right? While in NoSQL, there's no easy way to do this. If you had a separate table for, let's say, all the values of the addresses, then the information wouldn't be implicit. You couldn't force a constraint, like a foreign key constraint, which would say that this column 23 can only exist if there is a corresponding column in the employee table. So relations are not implicit. And the fourth and final problem, which is a major problem, is that joins are hard. If you have two NoSQL tables, let's say, then when you're joining those two tables, what you need to do is you need to run through every block of data here, find that relevant column on which you're joining to the other guy whose relevant column you need to find again, of course, and then you need to merge them together. Joins are actually all manual, so to speak, in a NoSQL database. There's no intelligence behind these kind of joins. You can try to improve on them, but there's only so much you can do. While SQL databases are to some extent built for joins. Yeah, inner join, outer join, left outer join, all the things that we didn't read in college. Those kind of things are very common when you're dealing with SQL databases because they have inherent relations in them. So these are the advantages and these are the disadvantages that we have of NoSQL. When do we actually use NoSQL? Well, it depends on these things, of course. It depends on if your data is a block and if you're making few updates and you want to keep all of them together, like if you're finding something which has to be write optimized. There's a lot of writes coming into that. Maybe NoSQL is the way to go. There are scenarios where you might want inherent redundancy or aggregations in the data, in which case NoSQL provides that for you in a really nice way. Of course, you can see all the disadvantages, and that's one of the reasons why applications like YouTube or Stack Overflow still don't use NoSQL databases. But it's really nice, and we are going to be taking an example of Cassandra to understand these databases in detail. So this is the Cassandra architecture that we'll be talking about. The requests will be coming into this Cassandra cluster, which is going to have 5 nodes, and it's a pretty expensive thing to actually host a Cassandra cluster. It's going to be having request IDs distributed in this cluster. So any request between 0 to 100 will be falling in node 1, between 100 to 200 will fall in node 2, and so on and so forth. So there are 5 nodes. And you can see that there's a request ID 1, 2, 3, so it should fall somewhere over here. Or rather, it should fall somewhere over here. So request IDs may not always be numeric. It might be a UUID, or it might be a person's name or something like that. So what we do is, instead of thinking about IDs in NoSQL databases, often things are considered as keys. So have a look at the sharding video to get a better understanding of how these keys are mapped. But basically, we just take the hash of 1, 2, 3. So it's passed through a hash function. This might be a string, this might be anything you like, and we get a value. So I'm going to take that as 256. So this hash is then used to map this request to a particular node in this cluster. So 256 falls between 200 to 300, so it falls over here, right? Or rather, I should take it as any place that it falls. I'm going to take the clockwise next node. So I'm going to pick up 4. So if the hash function is nice, meaning that it's uniformly distributed, what we can assume is that if there's a lot of requests which are coming in, then they'll be falling with equal probability in any of the nodes. So all of the nodes should have approximately equal distribution, 20% of the load. The advantage of this is that if you have a lot of requests coming in, and you want to, of course, make sure that all of the nodes are being used to their full capacity. So because there's random distribution, all of them will be having equal load, and they can actually go up to their full capacity instead of one node having too much pressure. When can one node have too much pressure? When your hash function is not really nice. So let's say your hash function is that anything less than 100 is equal to 0, and anything greater than 100 is 1. So what will happen is all requests greater than 100, which is from 0 to 500 we said, so that's around 400 of the requests will fall in hash function 1. So let's say it falls in 2, and the other requests fall in 1, and the rest of the nodes are not even touched. In this case, what's going to happen is, the moment you hit your load for 2, your entire cluster is going to be fully loaded, right? Because 2 is going to crash. So to avoid this, you need a good hash function. Or if your hash function is bad and you can't change the hash function for some reason, maybe you can't do a hot change of the hash function, what you can do is you can do something like a 2-layer cluster, where when the request goes to 2, it doesn't actually store it in its database. Instead, it sends it to another cluster which has 5 nodes, and you pass a different, you run this request through a different hash function. So h dash, which gives you a different value. So this hash function sucks. This hash function can be really nice, uniform distribution, and therefore these 5 nodes will have approximately equal distribution. And using this technique of multi-level sharding, so to speak, just have a look at the sharding video. Multi-level sharding, you should be able to survive. But of course, this is not a very good idea. Why have multiple levels of hash function? Well, why not? If you are a user, let's say, of Google Maps, and you're in India, then maybe your hash function over here is hashing on the basis of country. So the country ID is the only thing that you're looking at. And based on country ID, if you're sending it to one place, it's possible that one of the countries is going to have a tremendous amount of load for certain festivals. Let's say Diwali, everyone is using Google Maps, everyone is going somewhere. What will end up happening is this node will have too much pressure. And in those cases, what you can do is go for multi-level sharding. All right, so these are the major advantages of using a hash function. The thing that comes in very intuitively with a hash function is that you have a node where you're going to be sending the request, let's say 2. And you also want to make sure that this data is persisted in a way that you don't lose the data if 2 goes down. So Because this is important data, if 2 crashes, you don't want this data to be lost from the entire cluster. So you want to make copies of it. You want to make replicas of that data. Who do you choose to have those replicas? Because of this hashing concept, you can just ask 3 to also have a copy. Any node after 2, if it falls on 2, if the request falls on 2, any node after that should have the copy. If the request falls on 5, 1 should have the copy. You have 2 nodes which are storing the data, which means that the probability of you losing the data is lower. And also when a person is making a query, what you need to do is you need to hash it, hash this request, figure out where it falls, and any one of the replicas can actually answer. So if you are making 2 replicas, 1 or 5 can answer. If you're making 3 replicas, then 5 or 1 or 2 can answer, and so on and so forth. So your read queries are optimized. Your writes are also more guaranteed, and it could also be optimized because if 5 misses the write, then you can just write it to 1 and still working. So through this, Cassandra gives us 2 features of load balancing. You can have a look in the description for a good link for this. It's a system design playlist video. And the second thing is redundancy. So redundancy, or let's say replication, they're slightly different, but this gives you data guarantee and this gives you speed in reading. So because like we said, we are going to be distributing the reads and we are going to be making sure that the writes happen really well. We have both of these features in the Cassandra cluster. One of the very important concepts when it comes to NoSQL databases is the idea of distributed consensus. What I mean by that is that there are 5 nodes and let's say the replication factor is 3. So if a request falls on 5, then 5, 1 and 2 are going to be copying that data. They need some sort of mechanism to agree on a particular value to return to the user. Why is that the case? Well, let's say I write on 5. So there is some data appended here. Concurrently, I'm going to be writing on 1 and 2 also. However, let's assume that 1 and 2 are a little slow, so they actually haven't got the write yet. If that is the case, and I make a read operation now, so let's say I added my profile on 5, I'm expecting 1 and 2 to have it too. I make a read operation on my profile, and 5 crashes. Nothing to worry about because 1 and 2 should be having all the data that 5 should. So I go to 1 and I ask for my profile. I see that it doesn't exist. 1 returns an error. The application now assumes that this profile doesn't exist, so it returns a user not found error. So I'll get confused that I just made my profile and why isn't it there on the database? To avoid these kind of issues, what Cassandra should be doing is returning a database error so that the application knows that there's something wrong in the database and tells the user that, hey, there's something wrong with our database, wait for some time. Okay, so to do that, what we need is some sort of distributed consensus. And one of the ways to achieve this is Quorum. Okay, Quorum is a way in which multiple nodes who are related to a particular query accept a particular value, or they come upon or decide or vote for a particular value. What I mean by that? Let's say 5 did crash. We went to 1. 1 said, I don't have this data. And 2 said, I have this data. Let's say the concurrent writer happened. If that is the case, I will be picking up the data with the latest timestamp. Okay, the version ID, the timestamp, whatever you like to say, and returning that to the user. In this way, the user is happy that their profile is created. However, let's assume that even 2 does not have the profile created yet. In this case, both of them will agree that there is no profile created. And unfortunately, the user will be given a no user profile found. If the quorum value is equal to 2 and the replication factor is equal to 3, that means that if 2 of the 3 nodes, which means a majority of the nodes, accept a particular value, then we take that to be the truth. So in this case, unfortunately, if 1 and 2 both don't have the writes replicated on them, that will result in a wrong error sent to the user. So do we mind this? Little bit, but this is really rare. The possibility of 5 crashing and 1 and 2 not having the writes before they get a read operation is really rare. So this is a risk that we are willing to take when we are taking a NoSQL database and just move forward with availability instead of consistency. But what are the other good scenarios? I mean, the other good scenarios are that 1 has it, the timestamp is more relevant, so 2's data won't be taken. Finally, maybe both of them have it. Why don't we become optimists as engineers? So that would also result in the correct data being returned. And that's the reason why quorum is an important concept. What it allows you to do is take a risk, but in most cases it is correct. Right? A quorum of 2 is highly unlikely to fail. What if I make it a quorum of 3? Like 3 nodes have to agree with a replication factor of 3. In this case, this query will fail because 5 has failed. You need 3 nodes to agree on a particular value. 1 and 2 don't agree. 1 and 2 will return a particular value, but 5 is not returning a value, and therefore the query fails. I'm also taking a special case where I'm picking up the latest timestamp. If the quorum factor is equal to 2, it's very, very likely that unless both of them agree on some value, you're going to fail the query. Okay, I have taken timestamp because in this case, it clearly shows that you can still work around with 1 and 1 versus 1. Basically, there's no majority, but most of the times it's going to be they don't agree on a value, just fail the database query and tell the user that we are unavailable for some time for your particular request. Now, if you want the details of how a quorum work, I'll be taking a video on this a little later. It's distributed consensus, so there'll be Paxos, there'll be the gossip protocol, but in general, you can just assume them to be sending all their information to a central server. Yeah, let's say 3 is the person who they all send information to, and 3 then counts the votes and then chooses one value and returns it to the user. Now, what happens if 3 fails? That's a master, so to speak, in this cluster. There's distributed consensus that we'll be taking in a future video, so that should answer that. The final way in which Cassandra stands out as a NoSQL database, even Elasticsearch has this feature, is the way in which it stores data and the way in which it writes data. So if you have a request coming into Cassandra and you have this key value pair, assume this table to be existing in memory, right? Because you need to write it somewhere. So Cassandra will be storing all of these records in memory as a log file. Okay. The reason I'm calling it a log file is that whenever there's a request for some write, it's going to be writing in a sequential fashion. So if a new request comes in, it goes to the next point. New request, next point. In this way, you are actually storing all the data like a log. This is efficient because all you need to do is go to the point where you have the current pointer and just write down the data instead of searching anything. Okay, so this is fast. And periodically, this memory is dumped into something called an SS table. So sorted string table. Why is it sorted string? Because the key is sorted in this string table. So if I have some data over here, so the key is going to be sorted and the values are going to be per key. Now this is persistent storage, which means that it's going to be stored in one of these cluster nodes. This concept comes from a very famous Google paper, which is the big table data structure that Google made. You can have a look in the description below. But the special thing about a sorted string table is that it is immutable, right? So this data is not going to change. It is immutable. So every time Cassandra has some data in its memory, it flushes it into a new sorted string table. Now you can imagine that because these requests are coming in after a few days, what's going to happen is you're going to have a lot of sorted string tables all over your cluster. And these are going to be taking up a lot of space. Why? Because any update, let's say the key is 123, and 2 days later you got an update on that key, 123. So some data in that has changed. Maybe the name has changed from John Doe to the middle name has been added. So in this case, what's happening is you have an update on that key. The latest record is this record. It's in some other sorted string table because that was created later on when it was flushed to the SST. And effectively what has happened is you have multiple records for the same key, right? If you have multiple records for the same key, it's not a problem. The thing is you can always use a timestamp. This record will have a timestamp and you can use the latest timestamp to get the data. The problem is not consistency. The problem is data usage. Like you're going to be using a lot of storage with these duplicate keys. So if you have 10 records for the same key, then you are using 10 times the storage required. So Cassandra and Elasticsearch provide a feature called compaction. What we do is we take different sorted string tables and we merge them. So you can imagine this to be a merge sort. Yeah, you have 2 sorted arrays and you're just merging them. So this is an order n operation, and it's also the space complexity is the minimum of m and n, where the size of the 2 arrays is m and n. I have actually taken this extensively in the timsort video, which nobody saw. If you just want to know how this works, it's just the merge sort algorithm. If you want a detailed explanation of why the space complexity is so low, you can have a look in the description below for the Tim sort video. So that's the important thing. Basically, we have sorted string tables which are immutable, so they are really fast to flush into disk. You don't need to worry about whether they are duplicate keys or anything. And later on, like a batch process, you're going to be compacting these SS tables to optimize for space. How do you get rid of deleted records? Well, you can go to the deleted record, and Cassandra calls it a tombstone. So you place a tombstone, you probably set a flag, and the tombstone says that this record is dead. Yeah, any read operation on that, if there are 3 or 4 records and there's a tombstone, so you see tombstone on the latest timestamp, you call this record to be dead, and all 3 of them are killed. If there's an update on that key, again, if you see a tombstone, then you know that an update is impossible, and therefore you fire an exception, like record doesn't exist. So in general, this is how NoSQL databases work. We have picked up an example of Cassandra specifically, but there's a lot of concepts that are actually extensible to Elasticsearch, extensible to Amazon DynamoDB, and so on and so forth. There's a lot to digest over here, and if you have any doubts or suggestions, then you can leave them in the comments below. If you like this video, then hit the like button, and if you want notifications for further such videos, hit the subscribe button. I'll see you next time.